speaking. Don's going to be speaking some more. You're on, Don.
So I had delusions of grandeur of a talk using the Core One as a basis for AI in fourth, and I don't know. I was getting writer's block or something. I got a lot of stuff in here, and it was I don't know. I just had trouble formatting it to the page, so I'm going to just kind of do um, give you a couple of things that I worked on this month. So. um, I was doing a lot of research in neural networks, and all these neural networks use floating point. And I'm not a fan of floating point because it's not a natural language for a computer. I, I like I like integers. I think they're just great. Do scaled arithmetic kind of stuff. So I was thinking about okay, so they want they want more resolution on the number, right? Because they're using floating point. So I said, I wonder it with the FPJ that we're using, which is an 85 KLUT FPJ, and you can get up to 1 million KLUT FPJs. They're actually affordable up to about I think about a half a million. But anyway, I was curious. We parameterized the data bus width on the Core 1 at 32 bits. So I started playing with that, and I found I could actually increase it to 160 bits and still fit in the 85 KLUT. I would just curious. There's no way in hell that you would ever do that because it would be inefficient. What you really want to do is you leave the fourth computer at 32 bits, and then you create another core that would maybe do the computations of, for example, neural network weights, which are much wider, bit resolution. Maybe you want to have 64 or 100 bits of resolution, and you would just make an always statement, which makes it a coprocessor, or actually just make another Core 1, but it's just a micro-coded Core 1, and add the instructions and make the system whatever size you want, and the answer, so that would encapsulate your neural network, and then the answer you could tie it to the fourth processor over, say, a 32-bit shared register or bus. So it was interesting that I was able to make a 160-bit computer using the Core 1. Another thing that's I've been kind of playing with is, where are we? Oh, I'm not sharing let me share my screen. Okay. So let's see what's going on here. So I've been playing with Bard as a programmer. Wait a minute, wrong place. Okay, here we go. Can I get rid of this thing? Oh, like that. So I've been asking Bard to write code, and I was curious about what he came up with. Um, so one of the things that neural network guys like to use a sigmoid function, to calculate the weights in the neural network. So I asked Bard to write a sigmoid function in system Verilog. Let's see what he did. Okay, so this is a first time I tried it. This is the code he came up with. Um, so what I did was I copied and pasted this code over into our project, and I got an error that it didn't know what EXP was. That's this one here. So I went back to Bard and I said, okay, let's see. And I said, okay, write me system Verilog for the EXP function. So he wrote this code. That's basically it. So the system Verilog tools, I went and copied and pasted that. And it didn't like this at all. So I just set it to 1 and I was able to synthesize it. So I'd have to write something to calculate this in a function. But you notice that this is a function just like you would see like in C, and um, and then you're able to, it's kind of like a word in forth, right? So encapsulates this, and you can just call the function with its parameters in code, but it synthesizes the circuit. So this all did synthesize. I just have to write the exponent kind of stuff. Um, so it's very interesting. You can ask, okay, so I had asked it to write a function as a task. So you can have either a task or a function in system Verilog. And here's the task version. And then I asked it to write a functional using a function. So here's the function version. So what's interesting about using Bard is it gives you a starting point. It doesn't give you, actual synthesizable code necessarily, but it does give you a starting point. So I'm thinking about people that use the Core One when I have the dev board all done and we're getting this in people's hands. And by the way, you can buy a $30 board and play with it today. I think that using Bard to write snippets of system Verilog code is a great way to start writing your own opcodes on the Core One. You start with Bard, and you go and you see it's got some registers up here. So you go and create the registers, and it tells you what the function is. And it's a great place to start, coding in system Verilog. Let's see. So I'm going to ask it to write system Verilog code for expert system. I've done this before. It's very primitive, but it's very interesting in that it gives you a starting point. So, if you try to learn system Verilog, you'd be running around, taking the courses and reading up on what is a module, what is always statement, all this stuff. But it gives you this nice template, to get started with. Now, it's not 100% sensitizable, but it's a great way to learn maybe bad system, but you got to tweak it to make it actually synthesize. So the tools will actually, throw an error. Let's go back here for a minute. So this is what Bard said to use right here. And I'm going to synthesize. And you're going to see we're going to get an error. It would be great if you could just copy paste and it would work. But it's not a bad starting way to start learning system Verilog. So now it says exponent with more than one variable is not allowed. And it tells you the line number, 372. So it gets close to the line number. It's actually this one here. So now I basically, I tested it by just making this a 1, right? And comment that out. And then we rerun it. So while I'm talking, you'll see that it does get all the way through and synthesize. So this is a way to kind of debug your code. If it's complaining about something, just make it simple. Just set it to a 1. And it means that I have to code this. So what I probably need to do is to make a new function and figure this out. But now it will synthesize. So that's kind of a way to use Bard to get started on system Verilog. I did make some additions to our code, and what I did was I added 10 general purpose 32-bit registers, and I created some opcodes to store and fetch. Let's see. Where did I do that? No. Okay, here it is. Maybe not a great terminology, but I called it local store. So I created an opcode that stores in local register number 1. So this is actually I created an array of 32-bit registers. So this is storing in location 0. It's yeah, so you put the you put the number on the stack, and then it'll just get stored in there. So I added those, and the idea there is you can, instead of doing all the the stack stuff, which is the hardest part of learning Forth, swap, drop, rote, all that over, not under, but they can just load a register and they can use that to pass parameters. I know it's not Forth style, and if you're a Forth programmer, you would hate that. But if you're a newbie, it would be really easy, and the code would be very readable. So I added that. I also, let's take a look at this state machine. So we have the state machine in the outer interpreter, and it's got idle, parse a word, before link, get link, search. That's searching the dictionary. Add, exit, get executed token, number. So that's the way the outer interpreter is designed. You got to execute and compile. So we have these different functions in the state machine that is the outer interpreter. So I thought it would be nice to create some opcodes. So these synthesize. So here's an opcode that outer interpreter state set. So you can set the state of the outer interpreter using this opcode. You put it you put it on the stack, whatever the state is. You look at the enum, whether it's 0, 1, 2, 3, 4, 5, 6, and you would put it on the stack, and then you would call this word. Remember that our opcodes are callable just like words. So they're essentially fourth words as well. So you can set the outer interpreter state, you could set the compilation state, you can get the outer interpreter state. So these are some enhancements on where we're going. But Dimitri's been really busy the last couple of months. He's been taking a course, but his course just finished up, and we're going to be tweaking the outer interpreter quite a bit. He's got some new ideas on how to implement it. So he's going to be working on that. It'll be more fourth like. It will support immediate words. We don't support immediate words today, but it will support immediate words. And we'll break out like word, I mean the fourth word that's in the outer interpreter, and they will be separate opcodes so that you'll have access to all of the outer interpreter words you normally would have in a fourth. So that's where we're at with that. Let's see, any changes in the, I don't think so. So I'm still wrapping up the board. Pretty close. Pretty close to being done, but you know how that goes. The last 10% of your board layout takes a lot longer time than your first 10%, because you have to move traces around and stuff like that. It's pretty packed right now. So I'm still tweaking the board layout a little bit. I'm hoping by the next meeting I'll get them in, but it could be August when I send the boards out. So I would, if you're planning on it, I would probably think more towards August. And of course, we're not going to send out boards until I have thoroughly, tested them out, make sure all the circuitry works. This is a complicated enough board that I'm not expecting 100% success, but hopefully I'll get 98. If all the major systems work, like the ESP32, and you can program that, and you can program the FPGA, then that would be good enough where I would send a board to, say, Brad, or someone who's doing more development work, so he could play around with the ESP32 on there. And that's pretty much it for me. Anybody have any comments?
Yeah, Don.
Yeah.
All of the neural. That's why I learned APL. Was spent the 70s trying to understand get an inkling of how you go and make a brain, if you will. And one of the things, neural nets don't require much precision. I mean, consider that neurons are just essentially pulse width coded analog things. But what you have is essentially a dot product, an inner product that they're forming, and that's the fundamental computation. But so you have, in addition to summation function, verb, and a multiplicative one, and the sinusoid, not the sinusoid, the sigmoid is really traditionally that multiplicative function. But I put in the notes, I've seen some articles on a really simple function that works better than a sigmoid.
Oh, great. Put it in the chat. Put a link.
It is. It is.
Okay.
It's essentially, it's just essentially the value greater than zero. If essentially, okay, you move that threshold, but below the threshold, it just returns zero. Otherwise, it returns the value. So it's a linear function above zero. And that is anyway, if you do some searches, you can find, but also, by the way, the idea of having Baird go and give an example, because the best way to learn a language is to see some, so very, very interesting.
Yeah,
that's oh, go ahead.
Yeah, I finding Baird is a great place to start for a newbie in a new language, although it kind of can, send you down the wrong road a little bit. You can't think it's your teacher.
Beware. I mean, without question. Yeah. Really. No, that's visible even from some of your examples, and just in general.
Brad, what were you going to say?
Yeah, just actually a little echo of Bob. I mean, in the chat, yeah, that a lot of contemporary stuff. The sigmoid is actually kind of less popular, and the function, Bob, is the community refers to it as ReLU, ReLU. It's a rectified linear unit, and that's actually been one of the key things that they found in recent years, is that the sigmoid wasn't the best activation function for a lot of cases. There are some places where it's still popular, but apparently this even simpler function has won out. And the other thing is there's a link to a paper there. The precision that's needed is not very high, and in fact there are even folks that have had success apparently with 8-bit fixed point or even like 3-bit log scale, where you just bit shift by 3. So there's I think there's even some papers floating around with Xilinx and others where, because of that, they've played with it on some of their types of hardware. So it's I would definitely not assume that you necessarily need 64-bit floating points. Almost never used actually for some of these big networks. It's at most 32 and oftentimes float 16, even for training. So
yeah, if you run across stuff, shoot me an email or something with paper links.
Yeah, definitely. Or two, or even going to some non-standard widths, like okay, 7 bits, but and as a matter of fact, it might be interesting to read a neurophysiology paper and see what the resolution of human neurons is. This is, it's yeah, but it's low. It's low. It's in that 7 or 8 bits.
I think another reason that you see some of these the sizes that you do in a lot of the networks that are out there is they're being influenced by what the GPUs can do, and so you're picking the data sizes that the GPUs have been optimized for. A lot of those are informed by use cases in graphics, where the precision you're going for is a float 32 because that was useful for positioning something in 3 space, for that mapping, or float 16 for high dynamic range color. And so they're not necessarily perfectly tuned for ML. They're tuned based on graphics use cases originally.
And what's beautiful about an FPGA, you can make it 13 bits or 9
Exactly,
bits.
exactly. Yeah,
You know,
you can pick the right size instead of whatever. Yeah.
Yeah, so I chose the sigmoid function just to I wanted to kind of show how you'd use Bard to create an opcode in the Core One. I was talking with Dimitri, and he's done some research as you have, and he brought up your what'd you call it?
ReLU.
Yeah, he brought that up. So, but yeah, if you run across stuff like that, Brad, please shoot me an email.
Yep.
And if nothing, to plant a seed. So yeah, we're still building this guy, and but I found it interesting that I could go up to 160 bits. That's really incredible. And
Flexibility to go either big or small.
I actually just big nums. I just want big rationals. Okay, give me big rationals. And I've seen there's this matrix. I can't remember whose name it's attached to, but it's essentially, I guess it's just a matrix of inverses. It's essentially iota and inverse. So in any case, it goes singular. It goes really singular, really fast. And I was impressed by a talk by Bob Smith, who wrote a NARS APL. You can go search for NARS, but he implemented big rationals, and he showed that if you're doing sort of near singular matrix operations, big rationals are the way to go. So it's and yeah.
One of the interesting thing about the 160 bits is I have times and plus and minus as opcodes. Now times uses what's called a MAC, which is a multiply accumulate. It's a special circuit that is spread out amongst the FPGA, and it's for doing multiply functions. And what limited me to 160 was I ran out of max. I actually could get much higher than that if I commented out the multiply function. So it's a very inefficient. There's no way I'd ever do that with the fourth computer. That's just stupid. It's waste less. So the fourth computer will remain 32 bits, but it was just a quick way for me to see, how wide we could make the data bus essentially in the system. The better way to do it is you create a core with just the inner interpreter, and you create your opcodes, using the same technique I just showed you. And you could limit, you don't need all the fourth opcodes. Maybe you're only doing about 5 or 6, functions on the data, but you can use that very high level mathematic expression that System Verilog knows how to synthesize. That's a key quote there. And make it an opcode, and then just you write in the bootloader a little micro-coded program to work on your data however you want, and that becomes a coprocessor in the chip. You can also go to straight Verilog and just make it an always statement, and not even use a microcore. So using, in my mind, especially for embedded systems, FPGAs are the way to go, because you're real time. You don't have any interrupts,
Impressive.
Yeah, you could chew on data coming in at 200 megahertz, and it's its own little dedicated processing hardware inside the chip that's dealing with all this data that's coming in, and then it chews on the data and it puts it in a register that the fourth computer just goes at its leisure and either grabs the data or you have a second register as the input to that function to manipulate how it's working. And you can make a massively parallel machine this way. And when I first saw the green arrays concept, I thought, wow, that's really cool. But then I started thinking from a hardware perspective, all these cores are limited. They have to be the same. I mean, that's the only way you could design a chip like that. But sometimes you need a 32-bit, or a 64-bit processing, and then you got to put the cores together, and they got to talk to each other, and you have to learn the language. The green array, there's a lot of language to move things around between these guys, and sometimes you have to give up a guy in the middle, some processors in the middle to get the data from one side to the other side. And I just think to build a complex parallel system, doing it on an FPGA is really a simpler way to go, and you can build a more efficient, chip that way. Now, there's no way that that it's going to have such low power consumption, and that's pretty incredible about the power consumption. But FPGAs can get pretty good. So anyway, that's my talk.
Hey, one slightly, I'm interested and have been looking, getting involved in the market in hearing aids. Just how big are these chips? There is some interface or standard that is essentially a chip size interface between chips, so you don't have like a board. You got, what's the size? What's the actual size of these FPGA in the smallest format, smallest chip format, if you're going to build it into a hearing aid?
Oh, I see.
Well, I just go on DigiKey and pick the smallest package. I could do that right now if you're interested. Maybe after the meeting, we could take a look at that.
Like 5 millimeters by,
They have really tiny ones.
You probably don't want to go to an FPGA in a hearing aid. You probably want to go full custom at that point. That was one of the applications for the intellectual property associated with Chuck's chip. Those people whose company, I always feel bad when I wear their T-shirt. Intelisys. I was going to say the company who should not be named, but we all know who they are.
Yeah, what Great Arrays really needs to do is, that hardware is really good for some application. I don't know what that is, but they need to find the application where it's perfect for, and kind of focus on marketing their chip there. I don't have the time to do that. I'm too busy.
I think that is their focus. I think that's
good.
what they're doing right now.
Right.
It's a full-time job, and I don't think they've been terribly successful. They've had some flashes in the pan and some false alarms, but I don't think they've got the killer app for that technology, for that intellectual property right now.
There's one out there. I don't know what it is, but
well, it may be hearing aids, but I'm sure that they're aware of it. But if you're interested in green arrays, you can contact them and try to get them to give us a how to get started presentation. Or you can get started with them yourself and tell us what you did. Maybe Dennis can do that for us in all his free time, right, Dennis?
I heard my name.
Yeah.
Um,
So,
I did hear something about hearing aids just recently. There's a new chip out. But unlikely from green arrays, I don't think. But
yeah,
you know,
there's a
don't-
lot of interest. There's a lot of interest in that area because right now you no longer have to have a prescription or a doctor involved in the loop of getting the hearing aid. You can get a hearing aid from Amazon or from the TV ads. And I've heard lots of big names in the audio business. What's those people down in Santa Cruz with the headphones, Plantronics and
Yeah,
Bose.
I've tried. I tried a $300 level one that had a smartphone interface, and fundamentally, these things don't even have a graphics equalizer, the equivalent of a graphics equalizer. Then I got these for $100, and they're sort of they're enough to keep. But then you get to the $1,000 ones. I mean, the amount of money available in this field is essentially unlimited. But this is the thing is my background was in visual psychophysics, but the transfer to audio psychophysics. I mean, I want to make something where on your smartphone you can go and design your auditory space, your auditory frequency, and then even handle multiple harmonics, or even actually go with AI, go and have it, go and know the individuals that are around you and just amplify them versus all of the background. I mean, so you know, how much can you fit I think the behind the ear designs are really the ones that are very open-ended in the amount of processing power you can have, you know. Anyway.
All right, are we ready?
In that project, give me, you know, get in touch.
Yeah, actually, oh, can I respond to that?
Sure.
Yeah, so very interesting project. I'm actually just in a master's program here for digital design and completed a 500-line Verilog program for measuring frequencies and duty cycles. So if you put your email in the chat, we can talk some more. Getting somebody who actually knows how the human brain works is a really important part of the whole thing. And then somebody who's a user too of the application is really good. This is Dan Golding's talk. So let me ask him a question. I'm really very impressed. I'm the guy who's posted Python links, who's posted all the comments on your GitHub server.
Yeah, I recognize your name.
Okay, cool. And I am really impressed by a bunch of different things here, but the one that comes to mind most strongly is this outer interpreter in hardware, right? And so I think the killer app for your design is FPGA debugging. Okay, and
absolutely. Yeah, you're singing to the choir. It's
well. Let's talk more about and what
the busy flag. So there's
two I got you. Yeah, got you. I understand the business. Let's stay focused on this first one. Okay.
Okay.
And so I don't know. Presumably everybody knows that FPGAs are a nightmare to debug, and it takes like one of my friends says like 4 times longer than regular stuff. And the problem is you just can't see what's going on in the FPGA, and every time you have to recompile, and even if you have a fast computer, it takes a couple of minutes. And as a software developer, incremental compile time is everything, right? So you just have your 4th CPU in there. Okay, and why is the 4th interpreter such a killer? Well, because basically your outer interpreter takes no memory, and memory is quite scarce on FPGAs, right? So if I were to put a basic interpreter, you know, I mean, God knows how massive a basic, you know, I mean, even if you go with a register machine and you go with a basic or a Lua or a Python interpreter, they're all giant, whereas you have this really tiny interpreter. And, you know, and the other thing is if you go to JTAG, first of all, JTAG is a nightmare to program. We just learned how to use it. God, who thought that one up? But that's on the outside of the chip. So it's not at inside chip frequencies, it's outside chip frequencies. So So I totally think the killer app for this is FPGA development, and AI is great, robotics is great, but play to your strengths and really focus on that as a market niche. Okay, so let's discuss that for a bit, and then I'll bring up the next topic.
Yeah, I 100% agree. I actually list that in my talks. Did you see my talk in May?
Yes, I think so.
Okay.
I don't remember exactly what you said on it.
Listed, it's going to make FPGA development really easy because it's instead of this big, how do you eat an elephant one bite at a time? So you create an opcode with your system Verilog code in it that you're debugging, and you can interactively, talk to the registers, right? Because you create an opcode.
Exactly, you've got access to everything.
Yeah, and you can see what's in the register that you're updating, and notice that, oh well, that's not the right data. Oh, it's not. It's stripping the high bit or something. You
download your test program to download your test program to your fourth interpreter. I mean,
right?
Fantastic. So, maybe we can build this guy's hearing aid faster.
Yeah, I working with the Core One, and I noticed the same thing. It's like, wow, this is, I don't have to use Model Sim anymore. Model Sim is a tool to test your code. So one of the second
Model Sim is a simulator for Mentor Graphics, right?
Yeah, the simulator, right?
Yeah, I don't quite understand why they use it even. So good.
I actually have been coding with FPGAs for a while, and I actually bring internal signals out to GPIO pins, and I hook my scope up to it, and I actually look at the signals inside sometimes. But
okay, gotcha.
One of the biggest problems that really gets people frustrated with FPGAs is the concept of setup and hold times and propagation delays. So you say, okay, I want my widget to run at 25 megahertz. So you set your clock to 25 megahertz, and you create all these always statements. They're all doing stuff in parallel, and you test it, and you get the wrong answer coming out of it.
Gotcha.
Where did it come from? What module is causing the problem? So then you have to go to Model Sim and say, okay, this always statement has to complete execution within the time period, which is equivalent to 25 megahertz clock. Oh, I go through like 3 dozen of these things. I find this one that's a little bit too long. Well, this is another thing about FPGA coding. Use semaphores.
Mm-hmm.
Have a done flag at the end of an always statement. But that's essentially what our busy flag does. Is you don't have to do any of that anymore. If your opcode executes in less than a clock cycle, great, it's fast. If it takes 3 clock cycles, don't matter. The engine stalls for 3 clock cycles until you're done, because you set the busy flag in every piece of system Verilog code. The first line is you set it to true, and then the last line you set it to false, and the inner interpreter will stall until the flag goes true before it goes to the next.
Oh, I see what you're saying. Got it.
Yeah.
So it'll stall for as many clock cycles. You don't even have to calculate the clock cycles. It stalls for as many clock cycles as you need it to.
Yeah, and the machine basically adapts to your opcodes,
right?
Instead of you trying to fit it in some arbitrary timing scenario, which is what all the microprocessor guys do. They're told, hey, this micro has to go at this clock frequency because marketing says we got to be 5% higher than AMD, and now they have to do tricks like pipelining. Pipelining is where you work on a piece of data maybe three clock cycles, right? And it gets really complicated when you're in that mindset. an FPGA is silicon. It runs so damn fast. And FPGAs run at about 250 megahertz. Their prop delays are about 2 nanoseconds, between registers. So by using the Core 1 concept for developing FPGA systems, it just makes it so much easier, and you don't have to fight the minutia. So
Right.
but when you said that comment in the on I think it was on AI and robotics, and I put the link in there. Everybody should join. So people are asking me, like, what board to use, where can I get the Git repo? So join AI and robotics. I have a whole comment in the featured section that tells you how to get started. Instead of me just giving you a little snippet, join the group. And
I didn't see that. I didn't see that article, so I missed it. So I'll look for it.
It's under the. I leave it in the features tab. You have to
Gotcha.
scroll to the right, because there's about 6 or 7 items in there.
Okay.
And then also I have links in there to YouTube videos describing, the project. There's a bit to it, and you really need to kind of go through that whole thing. I will put my email. If you don't have access to Facebook, I'll put it.
Yeah, it's okay.
And you can.
So
Send me
just
an
one
email.
comment. As a developer, my expectation is that kind of documentation is going to be on your GitHub site.
I don't consider us done yet, and so yeah, we're not well
That's the message
documented at the moment.
You're doing a great job indicating that on your GitHub site as well. So you're doing exactly achieving exactly what you wanted to. Good.
Yeah, but that's a good point. I'll copy that over to the GitHub site.
That'd be awesome. What I did for the microcore is actually, if you go take a look at the microcore site, I actually edited his GitHub page and put his introductory video right on the GitHub page. So his site now looks really very professional, his GitHub site.
I love his microcore project. It's really great. And,
hugely interesting.
Yeah, he's been working on it for 20 years. The thing that I wanted to get away from with the Core 1 is you have to have another computer, and you can correct me if I'm wrong. This is my perception of this project, because I haven't looked at it, but you have to have the meta compiler running on another computer, right?
I believe that's correct. In fact, I'm sure that's correct.
Yeah. Whereas since we have
It's worse
our
than that. It's
interpreters-
worse than that. It's a messy Docker installation. I mean, it's kind of a night. His software is a bit of a mess.
Yeah, so with us, you hook up a keyboard and a screen, or you use an RS-232 port. That's it. That's your interface. And that's where I wanted
really
to
good
get
point.
to.
The J1 also has a Python interpreter, which I think is really interesting. It would be interesting to port that to your stuff, but that's another story.
I would love it if somebody took upon themselves to build a Python interpreter on top of our system. So are you volunteering?
We can have that discussion offline, but actually I do know how to do it.
Oh, that would be you would be my hero. Dimitri and I are way too booked, with the core of the core project.
We need to have this discussion offline and not here. Okay.
Okay, got it.
I
Sounds good.
But I'd like to just go straight to Cozy and have an APL level vocabulary and essentially just leapfrog Python, because those people that are involved in the mass market languages can stay there. From my perspective, I don't have the time for that.
I would love it if you put Cozy on top of our system.
Hey, get some people that are interested. I mean, Dimitri is definitely one, but they got to go and form an organization here that's got a cash flow. That's without question my absolutely vital, I mean, there are lots of, I need, and boy, is that exactly the opposite of everything that goes into forming an interface that's for me, by me, and not giving a damn about interfacing with other human beings. So it's, except through accounting, except through the accounts,
So, well, okay, this is open source, open hardware. I'm going to make it open hardware. We're going to put the AI playground board up on, I think it's called Crowd Supply, and get a few bucks in the door. Is Dimitri's worked his ass off. I worked my ass off. But it's not a for-profit project. From the standpoint of the basic machine, it is a platform for people to learn. I really want to get forth out there again. I see this as a way, because it's doing things that the C guys can't do.
Definitely languages have to be open source up to the level at which you're doing something proprietary on top of it.
Yeah,
but
exactly. So
yeah,
we build up the
That's right.
system.
Agreed.
And people could copy my board. I did it in KiCad, which is a free software. So they can actually start with my board, for their project, and they could delete stuff and they could make their own board and build on top of it. And we need to get a community like exactly how Linux was started with Tollboys.
One of the things is that looking at the number of words, Cozy, the totality of Cozy, including the Riva, is 2,300 words, and without question, the array vocabulary, the dynamic array vocabulary, I think would not be more than somewhere. Well, I'll go and make it 50K, and you're talking about. There's something, and the core of it, which actually Sam Falvo, when he gave his talk, he really did zero in on the core of it. Is this tree structure, if you will, dynamically allocated lists. Again, and what Sam noticed is, yes, the real important code is recursive code that allows you to okay, I'm freeing this. It's that keeping track. Every word takes care of its own accounting, and when nothing is referencing it anymore, it's returned to its space is returned to the inventory. So
yeah, what are my long-term goals? I'm a Star Trek fan. I want to talk to this damn thing in English. So so the code that I will be writing on top of the fourth computer is going to be very natural language kind of code. I designed this robot and I sold 2,000 Whiskers robots into tech ed, and this AI playground board back there that I'm working on is would be perfect for tech ed, and get even kids in high school playing around with FPGAs, like Chris was saying. So there's a lot to do, and once we got the outer interpreter working, I knew we're gonna make it. So that was the biggest milestone in the project. It's all downhill from here. It's just getting, all the I's dotted and the T's crossed. Dimitri wants to take another run at the outer interpreter and basically factor the code and make those pieces that I showed you in the state machine, words or opcodes, which are words, so that we could create word, which is in the interpreter, and it'll make it easier to do create does. So we're still, this is still an R&D project today is not ready for, you know, sending out to people. But those of you that are brave enough, you can download the code at GitHub. And
Hang on. Hang on. Good morning.
does somebody have a question?
Somebody has to mute Dennis because I had a problem with my computer and
What? Yep. Hello. Hang
Oh,
on.
he's talking.
yeah. Brad, could you mute Dennis?
Oh. Oh, shoot.
So anyway, you're going to sell boards or devices?
Yeah, so you know they're not free, but and by the way, I'm going to be sending probably 6 of the boards out to SVFig for you guys to use in lieu of the Whiskers boards that people bought. Dr. Ting bought 2 boards. And anyway, so you guys can divvy them up. Brad's going to get 2. So I guess probably you'll have 4 to divvy up. I'll send 6 total.
Well,
And how much are
find
they?
out if anybody wants them before you send them.
Yeah, okay, that's a good point.
The only thing I can think of to do with one is to put it in the collection of 4th hardware that we might show off at Vintage Computer Festival, if I can drum up some interest in that. There didn't seem to be any interest in that, but hope springs eternal.
Well, the first
Let me
board
ask
is
you,
probably,
are you going to do some kind of jumpstart thing with a populated board available?
yeah. So I will be supplying boards for people. There's a place called Crowd Supply, and if you look at it, people are pre-selling circuit boards like this, and a lot of people are buying them. So at the point in time that I put it up there, that's when all of my design files will go in GitHub. I'm months away from it because I know I'm going to have to do another board spin. It's too complicated not to have made some mistake.
I'm
So there's
glad you realized that.
Yeah, so you can have a couple of the first boards for your demo, for your vintage computer thing.
No, I'm just saying that if you're planning on having a thing that might be a crowdsourced jumpstart kind of thing, you might want to get some advice and help from somebody that has done this before. I don't know if he'd be available or interested, but this guy James Bowman, who did the Gameduino and
I remember
its
James.
successors, he's built I think 2 or 3 different things that were Jumpstart products that actually delivered. And what is the company, Adafruit or one of those online sellers of stuff, sells his products, and it's a real product. You know, you can go out and buy it, and it's a real thing. It's not one of these devices or products that sort of peter out in the middle of this and are never heard from again, or if they're heard from, it's just to deride them on some YouTube video that nobody watches.
Yep.
I have another question for Dan Golding, if I can.
Mhm.
So, you know, one of the questions is applications for your board. So this hearing aid stuff is hugely interesting to me. But the other one that comes to mind is a web server. So the question is, what's the other strength of these stack machines? Well, context switching time. So if you look at the microcore, evidently what he does is he does a context switching in 4 clock cycles. And I think,
Oh yeah, we can do that.
I think you can actually do less than that. What he
Right.
actually does is, I think he takes top of stack and next step stack and puts them in registers, right? And that way, then what's the context switch time? You have to write those 2 out, but you can actually cache those in another in another register, and then you just swap the new ones in, right? You can even, have the two next ones to go from the other program. Okay, so you can do maybe single cycle context switching time. Okay, well, where do you need context switching? So the real advantage of these stack machines is context switching time. Okay, where do you need context switching time? Where you're switching context a lot of times. The one that comes to mind to me is web servers, right? So you have like Nginx can evidently serve like 10,000 clients. So what does it do? It grabs a few bytes from one client that come in over the network, and then there are no more bytes. It context switches, right? And so you can imagine a web server, right, that has the HTTPS stuff, the encryption. I don't want to call it encryption stuff, but the security stuff, right? And so FPGAs do that really well, and then it's got 1,000 different tiny stack machines because you get tremendous parallelism, and then you've got a web server that can way outperform any commercially available web server. So I think that might be a commercially viable application for, what's the killer app for your chip? I'm wondering what everyone's reaction is here, because maybe I just am totally wrong.
No, you got a good point. So we're using very low cost FPGAs. Even the 85K chip is a very low cost FPGA. It's about $40. So there's a FPGA that I like called the Polar Fire from Microchip, and it has 500,000 LUTs. So
how many of those devices do you get on that? 2,000, 500,000. So
it's a shitload.
So that'll be 2,000.
So
you'd
like
get 2,000. No, I think you got your math off, right? Because divide 1,000, you take 2,000 lots on 500,000, so you divide by 1,000. If it was 2 million,
oh, yeah.
Right? So it would be like 2,000.
Yeah, you'd get a lot.
Plus networking, but you have to network the things. So that's going to take up some space too. But still, okay. So say you get 1,000, right?
Yeah, and they have if you're doing something like a server, we can spend some money. For about $1,600, you can get over 1 million LUTs. Like 1.5 million or something like that. So, because it's just source code, and it's so easy to move. And we've done everything in source code. We haven't used any IP blocks,
right? Exactly.
At all.
Yeah.
So you can bring it up on a brand new FPGA really fast,
right?
And
so do you think that's does anybody here think that's a viable market?
Yeah, it's not what I'd be interested in myself,
right.
But definitely, if you wanted to go at it, I mean, we would definitely support.
Yeah, it's not where my interest lies either. But I'm curious.
But
I'm curious if that's a viable place to be or not.
Parallel machine. So this is all about being a parallelism. So I've also, in the last month, I've been digging into why the hell is my damn laptop so slow if it has a 2.6 gigahertz processor. I'm a hardware guy. There's no freaking way, right? I should see an hourglass anytime.
Right.
So I've been digging into this. DDR memory, the fastest memory, and somebody on AI robotics brought this up. It might have been you, Chris. I don't know. It was one of our threads. We talked about the concept of clock speed versus throughput. The throughput over the last 10 years probably hasn't gone up a whole lot. The imaginary clock speed has. Now, I did some digging on clock speed. You know how they do that? So they're measuring the processor running out of L1 cache, right? And they have 8 processors, and they multiply. They figure out, and of course it's a single cycle instruction. And then they multiply it by the number of cores they have. So every time they add cores, the clock speed goes up. But if you open up your task manager on Windows, you'll see that Windows runs off of basically mostly on one core. It's not really good at multiprocessing yet. Maybe someday it will be. So, and now the I'm going to get back to the DDR memory. So they made processors so freaking complicated because they've chosen DDR memory as main memory. DDR memory basically has a 4K window. They call it a page.
Mhm.
And they have a 4K register that you can get data out of it in maybe 25 nanoseconds. That board back there has 3 nanosecond, SRAM in it. And the other thing is, if you have to switch pages, so if you do a jump, you hit an if statement and you jump outside the page, it takes 5 times more time, or 125 nanoseconds, to switch to the new page. So what they've done is they've gone crazy on the processor design. They have a predictive algorithm inside of the processor to try to predict when it's going to jump outside the page.
Right, exactly.
It's nuts. It's crazy. I'm a KISS guy, so that's completely anti-KISS.
Well, and the other thing is the developer knows what software is going to be loaded next, and the developer has no control over that. So they've seized anyhow.
So now here's the other thing. Okay, your main memory takes this much time to access data. So if you just went and you were randomly reading data and you were jumping between pages, it takes this amount of time, right?
Mhm.
Well, the L2 cache takes this amount of time. But if your processor is running an L2 cache, doesn't it have to wait until it gets?
Yeah, so that's the interesting thing about this web server application, because you have a few bytes that come in, you know which chunk of memory, so that you can go out to the DDR, you can grab that memory. When all that memory comes in, then you can process those few bytes. So this application works well with that cheaper DDR. And I also have to say my exam on Monday is about SRAM and DDR RAM. So anyhow.
Yeah, the funny thing about Forth is that it needs so little RAM. You can use the hardware RAM that's fastest. You can use SRAM. 64,000 cells of memory is huge for a Forth program.
Right. Yeah, I think what you're doing is great.
Let's see. Some good stuff in the chat there.
So, Doug, about the processor speed then. So they just created their own fudgy number system to give you this expected through the L1 cache instead of multiplying it by all the processors that they have in there. Yeah,
So they even went crazier than that. They have L1, L2, L3 cache, and then DDR. So the L1 cache, it has a 1 nanosecond because it's like the memory on an FPGA. It's built with the same technology. You can access the memory inside the FPGA, which right now in our smallest chip, we're just using the memory inside as memory. We're not using any external in one clock cycle. Okay, so their L1 cache is inside the processor chip. Sometimes they put L2 cache in there, so they have a little tiny piece of that, and then they have a bigger L2 cache. So if they get a cache miss on L1, they look for the data in L2. And if they don't get that, then L3 is on the motherboard. It's SRAM. The L3 cache is the SRAM I'm using for this guy. It's on the motherboard. And then if the data isn't there, they go look in DDR. I mean, imagine the complication of all that.
Right.
So what we really need is a number called throughput, not clock speed, because and I remember I go back to the 8008 and the 6502 and the IBM PC. I've been through the entire evolution. And I remember we used to, the PC used to be pretty damn fast, and then they went to this DDR memory, and all of a sudden it slowed down, but Intel cranked up the processor speed. They kept, going higher and higher speeds. And, it's very slow. And the other thing about DDR memory is, the way it's made is it's a transistor and a capacitor. So you have to refresh the capacitor. So 2,000 times a second, the DDR memory has to update all of the capacitors in a bank of memory, and in each bank of memory. And when you're doing that, you can't access data. So there's a control line that tells the processor, I'm busy. So it's the slowest memory there is. And it's really funny that, so they'll rate them, you'll look at the DDR memory, it says, oh, it's 666 megahertz. Wow, that's fast, that's great. No, that's if everything is right, it's not refreshing, you're just reading out of, you're reading out of the buffer, and then they made the buffer wider. So they said, okay, well, they up their speed. All these numbers are just bogus as hell, in my mind, from a hardware guy.
I mean, if you're saying that, it's almost like it was an intentional selling the public a slower system. Whereas
marketing.
If they redesigned it, let's say for some, back end, high end, grant government thing, that they could just redo it so that it doesn't use this, slow access memory, and put in, their high speed parallel lines for maybe SRAM or something like that. And they would get away from all this delay factor of refreshing and banking and all this other stuff.
Well, remember that the code today is written in C. C makes huge binary files, so they need that memory. Fourth doesn't need it, so it can run on you can make faster hardware by using the faster SRAM. And SRAM's memory cell takes 6 transistors, whereas the DDR takes 1 transistor and a cap. That's why there's so much more, you get so much more memory, but it's a lot slower. So I am dying to run some benchmark code on this guy and then run that same code on my laptop, which I have a gaming laptop. It's very fast. It's about 2 years old, but it was up there when I bought it. It was to gaming. It's an MSI gaming laptop. It runs pretty quick, and I'm dying to run some benchmarks, write some Forth code, write a mathematical equation or something. Maybe the prime number processing might be a good way to go, and run it on this guy and run it on my laptop and see which wins. I have a sneaking suspicion this guy's going to win from a hardware perspective, but until we test it, we won't know.
Well, you could also compare it against AMD as well, and see what the difference between the Intel and AMD, even though they're similar structures inside, but different programming.
Yeah. Actually, what we should do is make an application that forces bank switching, so that it's accessing memory like every 5,000 address cells, so that we're forcing page switching, and that would even be more of a horrible comparison from the standpoint of it blowing the doors off the laptop. So maybe store data, you know, every 5,000th address, and then you know, go and retrieve the data and do some processing on it, then go get the next piece that is, you know, for 4K away. That would show the worst case scenario of the laptop system. And if you did the same thing on ours, it would, you know, it would probably process in, you know, with doing some math on it, you know, maybe 6 to 10 clock cycles or something like that. Whereas a PC might be hundreds. It's speculation, but
Yeah,
I've
makes
done a
sense.
lot of research, but on it.
Excellent.
Well, sorry my talk wasn't more interesting today, but
We enjoyed
it
it.
wasn't. Got to take a look at Bard. Yeah, Brad, you should tell us more about Bard because you work there.
Not on that project though. So
Well, you know what I thought about Bard when I first started playing with the coding aspect of it? That maybe Google created it so to make their programmers more productive. What do you think?
I mean, you know, my general sense is it had been, you know, the fruition of a bunch of work on large language models going forward. Probably the fact that it's got more coding stuff is just a sign of the particular data sets they trained it on and so on. But
well, maybe you can't answer this question, but inside Google, if you wanted some code, do you have an internal mechanism like Bard where you can say, right, you know, give me some code and it squirts it out for you? You don't have to answer that question.
Yeah, I don't know that I should speak to that point, but yeah.
Thanks for answering. Yeah, I think you know, Bard gets you on, gives you a template. You know, it's the version that we have access to on the outside world. It at least gives you kind of a template on how to solve the problem, and you have to work out the details. Like, you know, when I was trying to do the Samoyed function, it had that one function call, and my synthesizer go, I don't know what that is. You know, it's not system Verilog. And then I went and looked it up, and then I asked Bart to write it, and it wrote it. But of course, it was using some floating point in there too. You know, I go, thanks a lot for that. But you know, I could take what I have now if I really wanted to. You know, I'm going to delete that code. I just did it for you know, for us to have something to work on today. But you know, I could make that code work from where Bard got me started. You know, it would probably take me a week of searching around the internet and everything, you know, looking at the algorithm and figuring out the code and all that. It did it in you know, 30 seconds, 20 seconds.
Oh, that reminds me of the olden days when there were PC boards and a separate math coprocessor.
Yep.
And I always used to say that floating point is the work of the devil. I can prove it. That's why the math coprocessor runs so hot.
Yeah, I didn't like when I first heard floating point, I go, what? Why? So at Made in Space, you know, I designed the flight computer for Archinaut 1, and we used a RISC-V core from Microsemi, which is now Microchip. And that core took up like 5,000 LUTs. And then, and all it's doing is command and control. It's not doing any math. And the software group insisted on putting floating point in it, and it increased the amount of LUTs by, you know, it went from like 5,000 to 10,000 or 6,000 to 10,000, something like that. and we're doing command and control. You're not even, wasn't even any science calculation or any heavy mathematics. They just wanted it, so they could code it in C++ and use floating point, whatever. It's a machine,
Yeah. Well, years ago, I worked on a image processor chip, and a guy wrote a piece of code that was supposed to go in a mortar round. And this was a chip that was programmed in C and had all the pipelining and all the fancy stuff you could ask for, and you would hand optimize each little bit of code to execute in some minimum number of clock cycles per pixel. So this guy wrote this application in C and handed it over to me and said, okay, here you go, optimize it. And first thing I looked at it, it's like, okay, you need to get this to work without the floating point. Because he was completely unclear on the concept. But we digress. Are we pretty much done with the with Don or Doug or Dan, as others have called him today?
Just call me Mr. D.
I call you very prolific in your presentations, for which I'm very grateful. I'm glad you're willing to present. And all you other ne'er-do-wells that are not presenting, now would be a good time to examine your souls and think, why is it that I can't present at least a couple of times a year at SVFig, or at least think of someone that I'd like to have talk and tell Kevin about that. So yes, I think
I want to make one more comment. One more comment. So I put in the chat AI and robotics on Facebook. We are up to 230 people now. We kind of sistered up with minimalist computing. Ken Boak, who's a fourth programmer, started minimalist computing. He's got 12,000 people over there. Help get forth out there. Sign up for AI and robotics. Sign up for minimalist computing. Actually, in the featured list at the top of the page, I have a link to minimalist computing because I want to promote their site. We need to promote Forth. We need more Forth people in the group. I want to encourage C people and Python and everybody else to come to the group, and let's debate it. Let's let them write their code on their laptops, and we'll write code on either this board or Klaus's board, and we'll show them the difference. This is how we get Forth going again.
Yeah, speaking of that, I'd like all of you to subscribe to our YouTube channel and ask for notifications, and maybe pick out once a week or once when you can, go to a given video on the channel and like it, and maybe leave a comment if comments are enabled. I don't know, Brad, are the comments enabled? I guess we talked about this last month. I don't remember where we were.
Yeah, I believe
They are.
That's wonderful. And that, believe it or not, may boost us in the things that YouTube kicks out when people search for stuff.
I want to make a comment on your comment. So I've been presenting here for a few years now, and I've actually used those YouTube videos. You notice that some of my videos have very high view rates. It's because I promote it. I promote the video. So I'm talking to somebody maybe about a job or something, and I'll send them a link to the YouTube video, the talk I presented on SVFig. So it does help you if you give talks, on SVFig. It's not just, you're spending time and you're talking to, a couple dozen people or whatever. It's very useful to promote your career and to promote your ideas, because you give a talk on your idea and you run across somebody and you want to tell them your idea. It's like on AM robotics, sometimes we were talking about something and it's easier to just send them a link to my video, because I went into deep discussion on the topic. So it's very useful for people to have those YouTube videos sitting out there on SVFig. It benefits you.
Yeah. The other thing I'd like you to do is ask yourself, did I sign up on MeetUp for this meeting, saying I would be there? And if you haven't, go to MeetUp and join MeetUp. You can turn off all the notifications so you don't get any stuff. Travis Beeman is going to talk next month about ZEP 2/4, because that's the price of plugging your Facebook group.
There you go.
So if you look at your chat, Travis plugged his Facebook group, and next month he's going to talk to us about it. But this month, I promised to give a blurb. Let me tell you what happened. Are we done, Don?
Yes.
Thank you, Don. Round of applause. Everybody, click the clap button, or whatever it is we do on Zoom. I forget.
Yay.
Yay. Yay. Thank you, Don. I really appreciate the presentation.
Yeah, I love our meetings.
I do too. Witness the fact that we still continue them. But let me tell you what happened. Okay, we're now in Kevin's talk. Can everybody hear me okay? We had some problems with the audio. It seems like I never have any problems until I'm going to present. And then
we can hear you well now, Kevin.
And then, everybody's, we can't hear you. Oh, well, it's the same setup as last month, and that was no problem. Okay. So let me tell you what happened. I got an email from a friend of Tig's that said Dr. Tig's widow would like to give SVFig a bunch of some boxes that he left behind. I went to their house and picked up the stuff and brought it to the storage bunker, along with various issues of the Mountain View Press hoard from years ago. I'm looking for the exciting share my screen button. Share screen, there it is. It's in green. I see it now. Select a window. Okay, I gotta open a window for this stuff that I'm gonna show you. Okay, well, there it is. Okay, am I actually sharing that window now?
Yes, we can see it.
Okay. All right. So there it is. I'm trying to drag the window and it's not working out for me because my life is hard. It's the IQ test and my brain is shut down for the weekend.
Oh, we can see your PC port.
Yeah, I know you can. But the problem is that I took these pictures hanging upside down from the rafters because my sinuses were dripping and I didn't want to have to wipe my nose. And I'm trying
Too
to
much information.
I'm trying to get this window to be I can't find the controls to this window.
That
All
looks
right.
like a camera.
There's a camera daughter board stuck on this board, which I believe has an FPGA, and it was in this box with this Altera Quattrus 2
Yeah,
software
Quartus 2.
development system. If anybody's more interested in this than I am, let me know and I'll send you a link to all these crappy pictures. And speaking of crappy pictures, if I had controls, I could zoom in on this, but I won't. So we're gonna zip through these pretty quickly.
That's the programmer
There's
for the Altera.
Yeah, this is more stuff that was in the box with the Altera stuff. And this is the pencil box logic designer. And Ting was futzing around with some chip and some LEDs and some jumper wires and stuff. There's the power supply for it. And a bunch of stuff. There's a banner. There's a banner from Formal 1984, which might have been in Taiwan or something. Another banner from some Chinese activity. And that looks like a off-the-shelf Actel board, some jumper cables and stuff in a box. This is the P21 B6 from Ofeat Enterprises. I guess it's not clear to me how you get a chip with your logo printed on it. But there you go. It's an actual part. More stuff from the same box. An MUP21. Now here, I guess, were some exhibits from an actual trade show or something. This one's numbered 7 and it's in a little display case. I don't know if somebody knows what trade show or exhibit or whatever this is from. Let me know. I'm at Forther, Forther, at Comcast.net. I'd be pleased to hear from you. And this is another exhibit from the same show, MUP21. So this might have been like the history of 4 chips, and I have like a Novix and a Silicon Composers USB stick, and maybe a couple of other things that might be useful for some posited future Vintage Computer Festival exhibit. P21G. There's a memory card and buttons, because it's got to have buttons. There's an antique laptop of the HP Persuasion.
Yeah, but
Some
the question
handwritten
is,
notes.
what's on the laptop though?
I don't know. If you want the laptop to explore it.
Because it could have, you know, the software that runs a lot of that stuff.
Maybe.
If it's hooked up via the serial cable.
Yeah. I think that trying to get any of that stuff to run at this point is Dave Jaffe says the buttons could have been a Chuck Moore keyboard.
Didn't he have like 7 buttons at one of the formals? 7 button keyboard.
Yes, Quartic keyboard, I think is the term that was used at the time for such things.
That's a long time ago.
Micro switches attached to his knee, and he just went and put in the bytes that he wanted.
And if the technology had been sufficiently evolved, I'm sure he would have had them implanted. So,
He probably typed in hex.
so John, did you want to have the laptop to explore?
Yeah, I'd like to take a look at it and, you know, if we can
I'll
recover
bring it-
anything of value on it, then, you know, we can just redistribute that to anybody who wants it.
I'll leave that judgment to you.
Okay.
Hopefully you have the
I'll try to
login
remember
code.
to bring it along to lunch if you want to drop me a line to remind me before the meeting, that would be good.
Sure. Hey, Don,
once-
you were mentioning something?
Once again, I was going to mention that once again, Ting, for many years, every July 4th would have a barbecue at Stanford for the lunchtime during the meeting. And to celebrate that tradition, we're going to meet after the Zoom meeting in July at Armadillo Willie's and have some barbecue and talk about Ting and Forth and stuff. So any of you that, and that's 2023, by the way, for those of you who are watching this on YouTube. So this is another Actel board. This looks like an off-the-shelf device that you'd use to explore the Actel stuff.
Another FPJ.
P24, 4th engine from 2000. And through random chance, demo 16C is right side up, although all the rest of the printing and lettering is not. There's an Intellisys box. Another shot of the P24 E4th. And by that time I was feeling blurry.
Hey, there's your keyboard again.
And odds and ends of stuff. Another lattice board. And Novix NC4000.
Oh,
and a
that's
Harris. And a Harris RTX 2000.
cool. Oh, wow. Donate those to the museum.
I think they already have both of those, courtesy of John Riebold. But the thing is that stuff like that, they're kind of behind in cataloging, so it may not be in their index. But it
I
seems
just
like
had an idea. What if we
I wondered what that smoldering spell was.
What if we had an auction on this stuff? And so we give you some money for your expenses. Think about it.
I think that more in line with reality might be better to put it up on eBay for sale, you know, sort of an online auction. I don't know how long stuff like that can stay up on eBay though, so we may have like the Mountain View Press eBay store and make available for a 6-month period books and chips and old Heathkit H89s that might run forth if you could get them to boot at all.
As an example, I'd be interested in acquiring those two things, but I'd want to donate to the club.
You are welcome to them. I will send them to you. Send me your address and I will send you those 2 chips.
Does anybody else want them? I'll donate some money, definitely, to the group for them.
Donate or don't donate.
Well,
it's
I have to increase my donation to $50 now.
It's like Yoda, you know, there is no there's no maybe, either do or do not. But if you send me your address, that's the necessary donation to get me to send you those chips. You simply have to ask for them. I will, the next thing I will do, I promise, I will go down to the warehouse where the storage bunker is and dig them out and send them to you.
What I'm going to do is I'm going to frame them and hang them on the wall, literally.
That's awesome.
Because they're history.
Yes.
Yeah.
But there's no idea whether they work or not, you know, and like I say, any of this stuff that you see, if you're that interested in having it, send me your name and address and please, Don, do that. It's one fewer thing to sort out from the storage bunker. It may take me weeks to get my button gear, as John
that's fine.
Can tell you, but it just goes to show you. Let's see, besides John, let me ask you something. Besides the stuff that Dave is going to bring, I said that I would bring some stuff to the to lunch in July. Do you remember what that is? Okay, John, maybe the other one. Well, think of it and send me an email to remind me, because I'm senile. Just ask.
Does anybody have a good picture of Dr. King?
Yeah, go to the website. I think if you look at his obit on the webpage, there's a usable picture of Dr. Ting.
I'm thinking framing it and put a picture of Dr. Ting there too.
So you'll notice that these are collector's items because the logos were printed upside down on these 2 chips. All right, another little daughter board with a USB cable.
It's ESP, it looks like.
Yeah, probably. It's one of these, whatever this is. And I don't know about you, but it's noon and I'm feeling blurry, just like this picture.
Oh my gosh, that was a Whiskers board.
If you want it back, you're welcome to it. And with
actually have some.
but this is the one Ting had. It's got a
Yep.
particular value. All right, stop share. That worked great. All right, since it's noon, every month we have the ceremonial starting of the quarter, and at the end of the month we have the unceremonious ending of the recording. So Brad, if you'd pull the plug, please.